differential equation with initial condition is called what? Initial value problem. Initial value problem. Okay, I gotta move this. Okay, true or false? Having a smaller delta t yields a more accurate approximation when you're using Euler's method. True. And if dy dt can be written as some stuff with t's times some stuff with y's, what do we call that differential equation? Separable. You guys are good. All right, so basically, you're going to grade yourself. On your folder, next to today's date, you're going to put a number from 0 to 4. You get 1 point for each of these questions you got right. You get 1 point for writing your question on your note card. And you get 1 point if you took notes on the reading, but maximum of 4. So next to your name, put a score from 0 to 4 for your reading score for the day. Okay, so today we're going to learn an analytic technique for solving one small, tiny kind of differential equation. Okay, so it's a pretty neat technique, but it doesn't apply to very many differential equations. But we're going to learn lots and lots of techniques over the semester. Okay, so a separable differential equation is one that can be written as a product of some stuff with t's in it and times some stuff with just y's in it. So it looks like dy dt equals some stuff with t's times some stuff with y's. So to solve a separable equation, you put all the t's on one side, you put all the y's on the other, and then you integrate both sides. So this is why I had you do some review of integration techniques last class. So here's a pretty straightforward example. So I've got dy dt equals t over y squared. Put all the y's on one side, t's on the other. So I'm going to just sort of cross multiply, or think of it as multiplying both sides by y squared and multiply both sides by dt. So I have y squared dy equals t dt. All the y's on one side, including the dy, all the t's on the other side, including the dt. And then I take the integral of both sides. All right, so what's the antiderivative of y squared? Y cubed over 3 plus c, right? There's going to be a lot of c's floating around, so I'm going to call this c1. All right, and what's the antiderivative of t? T squared over 2. And I have to add an arbitrary constant to that also, so I'm going to call that c2. Now, to finish solving this equation, I just have to solve for y. Just have to get y by itself, and I'll have a function y in terms of t that solves my differential equation. Okay, so I want to get y by itself. So first I'm going to subtract c1 from both sides. So c2 is an arbitrary constant, meaning it can be any possible value, right? I can make c2 any number, and it would still be an antiderivative of t. So arbitrary constant minus an arbitrary constant, what do you get? A different arbitrary constant. So I'm just going to call it C3. I don't know what it is. But rather than letting my algebra get really messy by writing C2 minus C1, just give it a different name. It comes out to some new arbitrary arbitrary constant C3. Y cubed over 3 equals t squared over 2 plus some new arbitrary constant C3. Funny looking t, sorry. All right, and then I just solve for y. So I'm going to multiply both sides by 3. So I get y cubed is 3 halves t squared. And if you take an arbitrary constant and multiply it by 3, you get a new arbitrary constant. So instead of writing C3, 3C3, I'm going to make it a C4, new arbitrary constant. And then take the cube root of both sides. Okay, so y is going to be the cube root of 3 halves t squared plus C4. Why can't I just say, well, let's call the cube root of C4 some new arbitrary constant? Call it C5. Say it's the cube root of 3 halves t squared plus C5. Yeah, because you can't take the cube root of each piece separately when it's addition, right? Just a little algebra review there. So this is my function, y, that satisfies this differential equation, right? We could check it because we did a bunch of checking last class. We could check it by taking the derivative of this thing, replacing dy dt with that, and then doing t divided by that thing squared. Make sure one side equals the other. It's a solution. So that's how you do separation of variables. All right, we're going to set up a model for this mixing problem. It's going to result in a separable differential equation. So one of the first things you're going to do in your activities is solve it. But first we have to set it up, and it takes some practice to be able to do these. All right, so we have a vat contains 100 gallons of liquid. The amount flowing in is the same as the amount flowing out, so there's always 100 gallons in this vat. The vat is kept well mixed, so the concentration of sugar is uniform throughout. And then we have 2 spouts going in and 1 spout going out. So this is spout A, this is spout B, and this is spout C, describing what's happening there. So this is just describing how the amount of sugar is changing in there. And what we're trying to do is write a model for S, the total amount of sugar in the vat at time t, right? So S is really a function of time, right? The amount of sugar in that vat is really a function of time. So I'm just defining my variable here. This is the number of tablespoons of sugar in the vat. And I'm trying to write a model, a differential equation model. It's going to be a differential equation because what they're giving me are rates, right? How is the amount of sugar changing? Sugar water is flowing in that has 5 tablespoons of sugar per gallon, enters at a rate of 2 gallons per minute. So all these things they've given me are rates. So my model is going to start with ds dt. Okay. So the amount of sugar is changing in that vat. Sugar is flowing in through pipes A and B, and it's flowing out through valve C. So my total change is the rate in minus the rate out. So now I'm going to go back to the description of like how fast is it flowing in, how fast is it flowing out. Okay, so sugar water containing 5 tablespoons of sugar per gallon enters the vat through pipe A at 2 gallons per minute. So I'm trying to write a formula for ds dt. S stands for sugar, T stands for time. Tablespoons per minute would be the units here. So I need to figure out how fast sugar is flowing in tablespoons per minute. I have tablespoons per gallon and gallons per minute. Multiply them and you'll get tablespoons per minute. Okay, so I have 5 tablespoons per gallon times 2 gallons per minute. Gallons cancels, and we get 10 tablespoons per minute flowing in through pipe A. Let's analyze what's happening with pipe B here. 10 tablespoons per gallon, 1 gallon per minute. 10 tablespoons per gallon times 1 gallon per minute. Gallons are going to cancel. And again, we have another 10 tablespoons per minute. All right, and then let's think about what's happening when the sugar water is leaving pipe C. It leaves at a rate of 3 gallons per minute. So the gallons per minute is always like what we multiply over here. So this is 3 gallons per minute. But over here is tablespoons per gallon, right? I need to know how many tablespoons per gallon are flowing out. How many tablespoons of sugar? So how many gallons total are in the tank? 100, that's given. So I want to, out of 100 gallons, how many tablespoons of sugar are in the tank at any given moment? No, that's total. That's the total gallons in the tank. Some of it's water, some of it's sugar. 20? Where'd you get 20? Yeah, that's flowing in. Yep. What's the variable we defined at the very beginning? S. What does it represent? The amount of sugar in the tank at some given time t. Yeah. Right. So because we're trying to figure out how much is leaving here, we don't know because this is like at any random time. So we'll just say S tablespoons. There are S tablespoons of sugar in the tank out of 100 total gallons, and it's flowing out at 3 gallons per minute. So quick multiplication here, my gallons cancel, and I get S. I guess I could write this as 0.01 S tablespoons per minute. Yes. 0.03. Yeah. Because of the 3, I forgot to multiply. So it's 3S over 100. I'll just write that. Tablespoons per minute. So I know how fast sugar is entering, just sugar, right? Not sugar water mixture. Sugar is entering the vat at a total of 20 tablespoons per minute. And it's leaving the vat at 3S over 100 tablespoons per minute. So I go back to my differential equation here, and I'm going to replace rate in with a 20 and rate out with 3S over 100. And when I want to solve this thing to make it easy to solve using separation of variables, I want to make this thing separable. So I'm just going to do quick algebra and simplify this to just get a common denominator, and you get 2000 minus 3S over 100. May or may not make it easier to separate. I don't know. All right, so that's it for the lecture part. Your first activity is to find equilibrium solutions. I just want to remind you from last class, those are places where S of t is constant, where the amount of sugar stops moving. And if the amount of sugar is constant, what is ds dt? 0. So equilibrium solutions, you just take the derivative, which you have a formula for, and set it equal to 0. Right. And then step 2 is to solve the original differential equation using separation of variables, a new technique.